Okay, this is alternating series and more tests, day number 2 notes on the new and improved comparison test. Why don't you join me, guys, on my notes here. I'm going to skip ahead here. Okay, so let's go back to the original comparison test and see how that is now made more useful or more easier. I'm not an English teacher, but it's made more easier using the new and improved comparison test. Okay, so let's show that this series either converges or diverges using the original comparison test. So let's write out a few terms here. We know this will be 1 over 1 plus 1 over 4 plus 1 over 27. This is going to be the sequence 1 over n to the nth power from n equals 1 to infinity. Do you agree with those first three? Decent? Okay. I'm going to show that this sequence, or this series from n equals 1 to infinity of 1 over n to the nth power is going to be less than or equal to from n equals 1 to infinity of 1 over 2 to the nth power. Okay, but I want to rewrite that in a different way right now. Well, could I write this as 1 to the nth over 2 to the nth? Would that 1 still stay 1 forever? Yeah? So could I then factor that exponent out? Oh, that's lovely. Okay, and make this just actually be 1 over 2 to the nth power. That's called a geometric series. And will that geometric series converge? Yeah, if r is less than 1 and greater than 0, that geometric series will converge. So I know that this is a convergent series because it's geometric with r, which is equal to 1/2, and 1/2 is less than 1 and greater than 0. Therefore, that series will converge. Now, if I can show that that series is greater than or equal to this series, then I can show that that red series would then be convergent. Okay, this is comparison test. We've done this. We did it with integrals, but it's the same concept. So let's write out a few terms of 1 over 2 to the n from n equals 1 to infinity. We'll got a couple terms. I'm going to go 1/2 to the nth power. So the first term would be 1/2 to the first, which is 1/2. We got a problem, don't we? Uh-oh, hold on. Let's keep going. The next term would be, okay, the next term would be what? 1/4. What would the next term be? 1/8. What would the next term be? 1/16, etc. So it looks like after the first term, everything will be larger. So this is larger than this. This is larger than this. This is larger than the next term, etc., all the way down the line. I want that to be, here we go. Okay, I had a mistake. Originally it was this. I wanted n to start at 0 in both cases. That was my problem. If I want n to start at 0, that would throw an extra term in here. Okay, if that started at 0, if this started at 0, that first term would still be 1 over 1. And then the next term would be 1 over, then this would be 1 over 1. Oh, shoot. Okay. So, apologies on why I can't figure out where my mistake is right now, but the way this problem was supposed to work was that I was supposed to be able to show that this series will always, all its terms, its sequence will always be greater than these, and therefore, because this is geometric, that would be forced to converge, right? That's the comparison test. So I had to find, right, I had to take a function, I had to find a function, that's the annoying part, I had to find a function that would always be greater than the other, right? And then I could squeeze that down to 0, and I could show if the larger one converged, then the smaller one would converge. Okay, so let's go ahead and look at our new comparison test. Like our old comparison test was annoying because you had to do two things. You had to, first of all, um, find a function that compared to this and was always greater than it. Right? That's the hard part, right? When we did this earlier, when we were working with integrals, and I gave you something like n squared over n to the fourth plus 7, what did we do to find a comparative function to that? We dropped the 7, right? We dropped the 7, so we could say that this would always be true. And then we reduced and said that this was true, right? So there was some work to be done to find another function that would compare to it, that we knew either converged or diverged. The limit comparison test, we can just take a function that we know either converges or diverges, and we can take the limit of their ratios. It's kind of like the ratio test, but it's not. Okay, so I'm going to take the limit of the ratio of those two functions. Okay, and the function that we know the convergence of this function. What does that converge to? Well, it converges. It'll end up converging to 1, but we know that that converges. We're always going to put that in the denominator. So as I work my way through this, I'll show you some of the attributes of this. But instead of trying to find a new function and showing and comparing those two, what we can do is when it's not easy to determine what a function would be that compares to it, I can just take one that I already know, and I take the limit of their ratios. So I'm going to take 1 over n squared minus n, and I'm going to divide that by the function that I do know converges. Okay. How can I go about finding the limit of that ratio? Function given and function that I know the result of. Simplified, how would I do that, Victor? Multiply by the reciprocal, right? Okay, so if I multiply by the reciprocal, I'll get this thing. I'll get n squared, I'll get n squared over n squared minus n. Okay, which if I take the limit as that goes to infinity, what will I get? 1. Okay. Okay, now here's where the fun begins. If our limit ends up being a positive, it should never be negative, but if it ends up being a positive integer, or I shouldn't say integer, positive finite number, then the function that we're comparing to the function we know will act the same. So they will act the same. Okay, so what do we know about, so since the sum from n equals 1 to infinity of 1 over n squared converges, did we get a positive finite number? Yes. Therefore, since we got a positive finite number, then 1 over n squared minus n will also converge. It's going to act the same way as 1 over n squared. What if we get infinity? Well, it'll diverge. Okay. What if we get 0? Yeah. No. No. If we get 0, okay, now here's where it gets kind of funky. If we get 0 and the known function converges, then the unknown function also converges. So I could technically say, but I don't want to put it up here, but I could say 0 or positive finite number if the known function converges. Okay, so let's pause for a second. What if I compared it to 1 over n and I got the number 5? Does 1 over n from n equals 1 to infinity converge or diverge? Diverges. Therefore, the comparative function will also diverge. Okay. Yeah, Emma. Okay. Let's say I'm comparing some unknown function, right? Uh, we'll call it sum from n equals 1 to infinity of whatever sub n, right? And I'm comparing that to something that I know converges, like 1 over n squared. I know that converges. So I take the limit of the unknown over the known, and let's say I get the number 8. What does that tell me about the unknown function? That it is convergent. What if I get the number infinity? That means it's divergent. What if I get the number 0? It converges. Okay? But if I compare unknown function to a different function, let's call it 1 over n. What do I know about 1 over n? It's divergent. So if I get 13, green one will be divergent. If I get 0, convergent. If I get infinity, divergent. It's like flip-flopped, right? It's like flip-flopped. So with a divergent function that I'm starting with, right? Any of these numbers and right here would tell me the green function is divergent. With the if I use the comparative limit comparison test with the red function and I get any one of these numbers, it'll be convergent. Okay, and then on the opposite ends, it's the opposite. That really didn't go well. But I feel like a few of you might have grabbed it. Maybe.